So hi there. So in the previous part of the video, we sort of reviewed the notion of the derivative of a function of a real variable, and saw that an interesting interpretation of the derivative is that it's that real number with which we must multiply, let's say, an infinitesimal arrow dx along the x-axis. So it's that real number with which we must multiply this arrow in order to get the arrow dy on the y-axis, right? So dy is f prime x dx, and so f prime x is the derivative, which is the real, and we define it as a real number with which we must multiply the infinitesimal arrow dx along the x-axis in order to get the image arrow dy along the y-axis. And of course, if the derivative exists, then it is unique at the point x, which means it's independent of the direction we move towards the point x or away from the point x. So we could sort of step by an amount dx to the left of x, or step by an amount dx to the right of x. If the derivative at x exists, it's the unique derivative f prime x. So now let's try and generalize these ideas and think about these ideas on the complex plane. So let's say we have the z-plane here, and then we have the image plane, which is the w-plane, and then we are considering a mapping of the form wc, right? Okay. Now let's say you're at some point here on the z-plane, and you make an infinitesimal arrow here. Let's say it looks like this. And so this is the real axis, so let's label this as x. This is the imaginary axis, let's label this as y. This is the real axis on the w plane, which we label as u, and this is the imaginary axis, which we label as v. So we'll again assume that since we're talking about the derivative of the function, we'll assume that the function is continuous around the point z. And for us, that means that if we make an infinitesimal arrow around the point z, then this maps to another infinitesimal arrow under the mapping wz. It maps to an infinitesimal arrow in the w plane around some point w. Okay. So let's say we make a small arrow here dz from z to so you're starting at the point z, and you want to think about what is the derivative of the function at the point z, and you make an infinitesimal arrow here going from, let's say, z to z plus dz1, right? And maybe under this mapping, maybe the image of this arrow looks like this. So it goes from w to w plus dw1, right? Now when we think about the complex plane and compare it to what we just reviewed for the real axis, for the function of a real variable, there's one very important distinction, or one very important feature that gets added when we're talking about functions of complex variables, which is when we're on the real line, let's say the x-axis, and we're thinking of mappings that take us from the x-axis to the y-axis, then at any given point x, we only have two directions that we can move in. We can either move from x to x plus dx, or we can move from x to x minus dx, right? But on the complex plane, from a point z, we have an infinitesimal number of directions that we can move in. So we can move from z to z plus dz1, we can move in this direction, we can move in this direction, we can move in this direction. So there's a lot more sort of freedom in which direction we step away from the point z. Now when we sort of discuss the notion of a derivative of a function, and again, just to stress again, we are thinking about like these infinitesimal objects, because sort of derivative is a local property. So we are thinking about locally what's happening to the function around the point x, right? And in the same way, we are generalizing this idea to the complex plane, and we are saying, okay, let's study this mapping microscopically, which means, let's say we are at the point z, let's look at infinitesimal arrows that are moving from the point z, and then think about what is the image of these infinitesimal arrows under this mapping w in the w plane. And this sort of again this tells us a lot about local properties of the function, or how it behaves locally, right? Okay. So again, on the z plane, we see that we have an infinitesimal number of directions, And in general, what might happen is that for an arbitrary mapping of the form, let's say WZ, if we draw one arrow, say going from Z to Z plus DZ1, and let's say we have another arrow that goes from Z to Z plus DZ2, the image of this arrow might be some image arrow here, which goes from W to W plus DW2. And in general, if we try and generalize the notion of the derivative that we introduce for the function of a real variable, that the derivative is that real number with which we multiply dx in order to get the image arrow dy, and just sort of plug that definition of a derivative for a complex function, then we'll say that the derivative, if the derivative of the function wz exists, then we'll denote it with a prime, let's say w prime z. So if w prime z is the derivative at z, then it is that complex number with which we multiply the arrow dz. So that arrow could be dz1, for instance. We multiply an infinitesimal arrow with which we multiply, let's say, an infinitesimal arrow, dz to get the image arrow. dw, or in other words, dw, the image arrow, is w prime z times dz, and this w prime z is the derivative of the complex function with respect to z. So notice that this is just a straightforward generalization of the notion of a derivative of a function of a real variable, one real variable. So in that case, we have dy equals f prime x dx, and then this is a real number with which we multiply dx in order to get the image arrow. But in this case, we have w prime z, which is a complex number with which we multiply dz in order to get the image arrow dw. Okay, so let's say we want to define the derivative with this definition, in the sense that this is a straightforward generalization of the definition of a derivative of a function of one real variable, and let's say we want to define the derivative, we want to keep the same definition and see whether that makes any sense or not on the complex plane. So let's see what this sort of implies, or what this requires from us. So let's say this derivative exists. Now, so it is that complex number with which we multiply dz in order to get the image arrow. Now, for an arbitrary mapping wz, this could mean that, let's say, you step in the direction dz1, so you have this arrow that goes from z to z plus dz1, and then you might have to multiply, in order to get the image arrow dw1, you might have to multiply it with some complex number, let's just call it c1 times dz1. So so this particular arrow is dz1, right, because this is z plus dz1 minus z, which is dz1. So we multiply this arrow with the complex number c1 multiplied by dz1 to get the image arrow dw1. Likewise, in order to get the image arrow dw2, we might have to multiply it by some complex number c2 times the image arrow dz2. For an arbitrary mapping, it might happen that we have to multiply the arrows that emanate from z in different directions with different complex numbers in order to get the image arrow. Because there is no constraint on the kind of the function we are talking about. When we talk about general functions, there is no constraint to the kind of function that we can build up. And in fact, this kind of a function is something, in fact, this kind of a scenario happens with a very simple function, and we'll talk about an example where sort of this kind of a scenario happens, where if you move in one particular direction, dz1, then you have to multiply it with one complex number C1 in order to get the image arrow dW1, and if you move in another direction, you have to multiply it by some other complex constant C2 to get the image arrow dW2. Now, if we want a derivative to exist at the point Z, then what we are claiming is that we want these complex constants, or rather complex numbers. They are not constants because C1 here is implicitly a function of the point Z, and C2 is also a function of point Z. So if a unique derivative has to exist at a point Z, then what we want is that all these complex numbers with which we multiply the image arrows are all the same, and all those. So what we want is that C1 equals C2 equals any sort of, if this direction is denoted by Z plus DZN, then any sort of infinitesimal arrow going in any direction from the point Z should have to be multiplied by the same complex number at the point Z in order to get the image arrow dW. So what we want is that C1 equals C2 equals Cn, and if that is the case, then we say that a unique derivative at the point Z exists, and that unique derivative is denoted by W prime Z. Okay, so now it may sound a bit roundabout the way I've talked about this, but there's a particular reason why I'm emphasizing this approach. So let's just go over this again, what this approach basically means. Now, if you recall the notion of or the geometric notion of the multiplication of two complex numbers, then we discussed in a previous video, and I'll put a link to the previous video, that multiplication involves two steps. Multiplication of complex numbers, of two complex numbers, geometrically implies two things. There is a kind of a scaling, which could be a magnification, enlargement, or a contraction. There is a scaling and there is a rotation. Now, with the definition of a derivative, that the derivative is that complex number at the point Z with which we multiply an infinitesimal arrow dz in order to get the image arrow dw. Notice that this sort of definition implies a product of two complex numbers. And therefore, what we are claiming is that if at the point Z a unique derivative exists, then all these infinitesimal arrows have to be multiplied by the same complex number w prime z at the point Z in order to get the image arrow, which means that if the first arrow we considered, let's say dz1, and the second arrow we considered was dz2, and the angle between them is, let's say, theta, then on the image plane this dz1 has to be obtained, or rather dw1, the image of dz1 has to be obtained by multiplying dz1 by the complex number w prime z. This w prime z times dz1, this w prime z is independent of the direction dz1, dz2 or dzn. This w prime z only depends upon the point z, because if a derivative has to exist at a point z, it has to be unique and independent of the direction with which we move away or towards the point z. And this is the same idea that we sort of emphasized when we talked about the function of one real variable, that it does not matter whether on the x-axis you move to the right or to the left. If a derivative exists at the point x, it's unique and it's independent of the direction of approach towards the point x or moving away from the point x. So if the derivative at the point z exists, then the image arrow dw1 has to be obtained by multiplying the arrow dz1 with a complex number w prime z. Similarly, the image arrow dw2, this arrow, must be obtained by multiplying dz2 by the same complex number w prime z times dz2. Now, what does this imply? This implies that if you recall the definition of multiplication of two complex numbers geometrically, and this is the number with which we are multiplying these arrows dz1 and dz2, it implies that the image arrows have to be scaled and rotated by the same amount. So both dz1 and dz2 will be scaled and rotated by the same amount when we are plotting them on the image axis, in the image plane, which means that if the initial angle between them was theta, then the angle between the image arrows will also be theta. Because if you take this arrow and rotate it by some amount phi, and take this, and that phi would be, so you can think of w prime z as modulus of w prime z times an argument of w prime z. So let me get rid of this. So w prime z can be thought of modulus times some angle that w prime z makes. So let's just write this as times the argument of w prime z. And this is the same idea that we talked about for the function of a real variable, where we denoted dy as f prime x times dx, and we can write this as plus minus modulus of f prime x dx. Because on the x-axis there are only two directions, either positive, which is 0, or negative, which is an angle of pi. In the same way, when we are considering infinitesimal arrows on the z-plane, dz1, dz2 and dzn, or any of the infinite number of directions, all of them have to be multiplied by the same complex number w prime z. W prime z has a magnitude and a direction, and when we multiply two complex numbers, what this will do is it will scale the arrow dz1 by an amount modulus of w prime z, and it will rotate it by an amount which is the argument of w prime z. But w prime z is independent of the directions dz1, dz2 or dzn. It only depends upon the point z, location of the point z. And so all these arrows will be scaled up by the same amount. So this, the magnitude, the length of this arrow, for instance, the modulus of dw1 will be modulus of w prime z times modulus of dz1, right? Whereas the angle that dw1 makes, or let's say the argument of dw1 will be whatever angle dz1 was making with respect to the x-axis plus the argument of w prime z. So let's say the angle that dz1 was making is theta 1. So it's theta 1 plus, let's say the argument of w prime z is phi. So let's denote this by phi plus phi. In the same way, the magnitude of dw2 will be the modulus of w prime z times dz2, whereas the argument of dw2 will be, let's say dz2 was making an angle of theta 2, so with respect to the x-axis it will be theta 2 plus phi, which means that the angle between the vectors dw1 and dw2, if it was theta, so if the angle between dz1 and dz2 was theta, which means theta is theta 2 minus theta 1, right? Then on the image plane, the angle between dw1 and dw2 will also be theta, because the angle that dw2 makes is theta 2 plus phi, then minus the angle that dw1 makes is theta 1 plus phi. So if we subtract phi, it's plus phi. So when we subtract off the angle of dw1, then we'll have minus theta 1 minus phi, and this cancels out, and so we find that the angle between these arrows on the image plane is preserved. And this is a very, very important idea, because so first of all, this is what geometrically the derivative of a function means. It means it's that complex number with which we multiply infinitesimal arrows that emanate from the point z in any direction. It's that complex number with which we multiply these infinitesimal arrows. The effect of that multiplication is both a scaling and a rotation by the complex number w prime z. But since w prime z is independent of the direction of the arrow itself, any pair of infinitesimal arrows, the angle between any pair of infinitesimal arrows in the z plane, when you map it on the w plane, the angle between them is preserved. And this idea sort of it has very important consequences, because it ties together two very important notions, or two very important notions in the study of complex functions. One being analyticity and other being conformality. So let's start with analyticity. If for a function we can find a complex number, a unique complex number w prime z at a point z, with which we can multiply infinitesimal arrows from dz in order to get the image arrows dw, then that function is said to be a complex analytical function. So, for simply speaking, an analytic function is, or a complex analytic function is that function Wz for which a derivative W prime z exists, right? And geometrically, it means that this W prime z is the unique derivative at the point z, independent of the direction in which independent of the direction we move away from the point z. So simply speaking, this is the definition of a complex analytical function. And we don't have to always go back and check it geometrically. We'll derive some other sort of criteria on how to check whether a function is complex analytic or not. But yeah, so this is one sort of important definition to keep in mind, that an analytical function is that, a complex analytical function is that function for which a derivative at the point, a unique derivative at the point z exists, and that derivative we denote as W prime z. So what about conformality? A function Wz is said to be conformal if it preserves the angle between any two pairs of curves at any point z in the complex plane. Such a mapping is said to be a conformal mapping. So, given the definition of an analytical function that it will preserve the angle between these two infinitesimal vectors in the image plane, an analytical mapping is by definition conformal. So we'll talk a lot more about conformal mappings and its relation to analytical mappings in future videos, but for now I just wanted to introduce this idea of what a conformal mapping is, and we'll make sort of these ideas a little more precise in future videos. But for now, let's work a little bit more on analytical functions and the derivative of a complex function, and work out a few examples where example of functions which are analytic, examples of functions which are not analytic, derive some conditions to check for analyticity, and then we sort of get back to the idea of conformality and talk a bit more about it. So yeah, see you soon with more videos. Thanks.